Okay, hi everyone. So I'll start with the new chapter, some material on hash functions, and then discuss the practice quiz a bit. So this is a new primitive. One nice thing about it is that technically I think it's quite a bit easier than some of the ones you've already seen. So your practice from encryption and PRFs will pay off here. It's been an exciting story in cryptography, in particular because of attacks, unexpected attacks. So this was the announcement some years back when the currently most popular hash function called SHA-1 was broken, and that caused quite a bit of consternation across the community, lots of changes engendered, and so forth. And so we'll lead up to that, the story of how that happened. So hash functions are in the same realm of things as block ciphers, in that they're things that cryptographers design from scratch using kind of clever bit and number manipulation operations. And they have lots of different uses in cryptography. The most central one is compressing data. You can map a long input to a short output, and it has to be what's called collision resistant. But in fact, the uses go well beyond that as well. People have developed lots of these, and they've kind of come in series. So the first one was called MD, and it had 3 functions in it, 4, 5, and 6. For a long time, MD5 was the world's most widely used function, but that also in the end got attacked. This was a government standardized series called SHA-2, and its first function was the one we just saw. And then there are others where the number here indicates the number of output bits. So nowadays, the 256-bit version and the 512 are some of the most popular. And this is kind of the future upcoming ones. It is currently a standard. It is in use, but it hasn't quite swapped out the ones here yet. Where do we see these employed? Probably the primary place is in certificates. So whenever you go to a website, the server authenticates itself by sending you a certificate, which has a signature which ties its public key to its name. And hash functions are used to produce those signatures. So they're pretty central, and you're using them, again, every day. Hash functions are also the basis of Bitcoin. So what is how you validate coins in Bitcoin, the mining process, uses hash functions. And they're also used for authentication of data, key derivation, and many other things, for example, through HMAC, and thereby in TLS and other protocols. It's a little ironic, I think, in retrospect, that when they gave the name SHA, they meant it to stand for secure hash algorithm. And in the end, it wasn't actually that secure, at least at the early part of the series. Okay, so what is our security objective here? We're looking for a function which maps some large domain to strings of, let's say, some fixed length, say n bits. And think of n like 256 or so. And we are defining what it means to be a collision for this function. A collision is 2 points which lie in the domain, and where when you evaluate the function, you get the same output. So pretty intuitive, right? Just the output on these 2 inputs is the same, they form a collision. To be non-trivial, there's another condition that you don't actually pick the same points. That would be silly. Obviously, if x1 equals x2, h of x1 equals h of x2, but it's not really interesting. So our question now will be finding these collisions when we're handed some kind of function. And the first observation one we make about that is that you can always find these collisions. Why is that? Because the moment there are more inputs than outputs, more points in the domain than in the range, there have to be 2 points that map to the same output. That's what mathematicians call the pigeonhole principle. So for example, if there are 3 inputs and 2 outputs, then you can map the first input somewhere, and the second somewhere else, but then you're stuck. The third one has to go to one of these. So what we know from that is, as long as you have more possible inputs than possible outputs, there will have to be collisions. And the interesting cryptographic element here is to say that yes, these collisions are out there, but we will design our functions in such a way that they're hard to find. Hard to find means the amount of computational effort or time you have to invest in order to actually come up with a collision is prohibitively large. So it's kind of interesting that you can actually even do something like that. Okay, so now let's formalize this, and we'll do that using games. And again, as I kind of remarked at the beginning, these games are actually rather simple compared to ones you've seen, so hopefully quite easy to assimilate, although as we'll see, there's one new element. In this formalism, I'll generalize the previous picture a bit so that we're not talking about just one single function, but a family. We've seen families many times before. That's what block ciphers are, that's what PRFs are. We've seen through that different security notions for families, and here's another one. There's no difference in the syntax. You have two inputs. You'd regard the first as a key, the second as some kind of normal input or message, and there's an output in some space. And we remember that whenever you fix a particular key in this space, you induce a function from here into here. And you define that as just using k as the key and x as the input for h. So associated with that is a game called collision resistance. And as usual with these games, it starts with an initialize. And again, as usual, the initialize will pick a key from this space. But now comes the unusual step, which we've not seen before. If you remember key recovery security and PRFs, the key was hidden from the adversary, and the adversary's job in key recovery was actually to find it, and in PRF security to do stuff connected with it. But here, this return statement says, having chosen the key at random, I'm going to actually hand it over to the adversary. So your adversary upfront knows what the key is. It would be no point talking about key recovery security here. You're giving it the key. So what does it have to do? Its job is just to find two inputs which have the same output under this function hk. So there's no non-trivial procedures. The adversary just trundles along, and eventually it says, okay, here's my two guesses, x1 and x2. Please check that I'm correct. And the game will look at those and check the collision conditions. That means, first off, it checks you don't have something trivial. If these are equal, it says, no, that's just cheating. So there you lose. And then it checks whether when you evaluate h with this key on x1 and x2, you get the same output. And if so, it returns true and otherwise false. And that's it. That's all the adversary has to do, find two inputs with the same output. But given that there is some randomization in the choice of key, there will be some probability of success. So when we run the adversary with the game, this says, consider the event that the game outputs true, meaning the adversary found a nice collision. It has some probability, and that probability is the advantage of A. The CR tells you the metric, collision resistance, H because it's this H, and A because it depends on the adversary strategy. Okay, so this is going to be basically the security metric for the whole of the chapter. So again, any thoughts on that? I said it's a simpler one, so hopefully, yeah. Okay. So just some remarks to basically write down the things I said verbally. Whenever you see a return statement like this, it means your adversary gets this object. So in particular here, the key is not a secret. There are some things we don't write down but insist on, namely that the adversary's 2 points here must belong to the domain of the function. Remember, the function h has its domain D. If you provide things outside that, the adversary is considered invalid. It's because h sub k is not really defined. Okay, so let's see if we can test this out by breaking a few things. So I can pick some arbitrary h, and I picked this weird one where the set of keys is the numbers from 1 up to 2 to the power 256. So anything from 1 up to this number n. The domain I made actually infinite, so it's all again integers. And the range is numbers from 0 through n minus 1. And how is h of k and x defined? You take this input x and you just do a mod by k. It makes sense, k is a key in this range. So this is an integer, and when I take the mod, I'll get back something in this range. Okay, so that's a legitimate function family. So we can now ask, is it collision resistant or not? So what we're asking there is, you put on your attacker hat, you go back to these games, and you ask yourself, can I find a pair of inputs on which the output of h will be the same? And you remember by the rules of the game that when you do that, you actually know what the key is. So given the key, can I find such inputs? 2 points in this range with the same output. Okay, so any ideas? Yeah?
You could set x to 0 and then just set k, and well, for x1 you could just set it to 0, but x2 you could just set it to a multiple of k.
Yeah.
You get the same.
Okay, good. Yeah. So exactly. So, and in particular, one of the good things he did there is use the fact that as an attacker you know k. And this equation generalizes what he said, which is that even if whether you put x to be 0 or not, multiples of k or k added to x don't change the function output. Because if you add k to x here, well, when you do a mod k, nothing changes. And so that gives us exactly the adversary that he presented. So you set, say, one input to 0 and the other one to k. And 0 mod k is 0, k mod k is 0. And so you get back, so you return this as a collision. Now notice all the syntactical elements. There are some new things here that are good to do properly whenever you have to do this on a test, say. Notice that A gets an input of this key, and it's written like this. It appears as an argument. And that reflects how this return statement is seen from A's perspective. Then you have code, and there's a return statement here. This return statement should always give you 2 points inside this space. If it doesn't do that, it's not even syntactically valid. Once it does that, you can test whether it really is a collision and then compute the advantage. Okay, so that was a little bit of a naive example. It didn't even attempt to, say, leverage any crypto we know. So what if we said, okay, let's try to build something a little more seriously, where I'll use a block cipher. After all, I know I have good block ciphers like AES. Why can't I turn one of those into a hash function? So given my block cipher, I build a hash function. I leave the key space the same, but I want to hash 2 n-bit inputs. So if this was 128, I want to hash 256-bit inputs down to 128 bits. And now I have to think how to do that. So here's my attempt. It takes a key from here, and this x we know is now 2 n bits long. So the natural idea is, given that E takes n-bit inputs, I'll break this x into 2 blocks, each n bits long. And remember, this notation, which will appear repeatedly, says that this string is broken into n-bit blocks, and you have here as many blocks as you'll get out of that. The way the hash function computes the output is, it says, I will apply E with this key to the first block. That'll give me an n-bit output. I will XOR in the second block and apply E again. So effectively, it's the type of thing you do in CBC encryption, except in CBC encryption, you would output more stuff. It's like outputting only the last ciphertext. And that's what you return. And my claim is that it was a reasonable attempt, but even though you used a block cipher that could be strong, it actually doesn't work. And we'll try to develop some intuition about collision resistance by seeing why that's true. So any ideas, like how would you approach breaking this, or how would you break it or something? So I'll give you a start on how one usually thinks about approaching collision resistance problems. Namely, you want to find two inputs that have the same output. You know what the key is, and so you also know that each input actually has two blocks. So what we're really looking at is an input here which is 2 blocks long and another input 2 blocks long, and you get to pick everything here. So you have 4 things, if you like, that you can pick. And collision resistance can always come down or be viewed as some kind of equation solving. So what is the equation? That the result of H on the key on these two inputs is the same. And this is a succinct form of that equation. I've taken the formula and evaluated it on x1 and x2 and just asked that they're the same. However, I did do a little bit more. Namely, the formula evaluates this and then another ek, and I've just dropped the last ek. Why is that? Because if these two are equal, I'm done. Applying another ek is not going to change the equality. So now we can see this as the task. So you've got it down to solving this equation. In solving that equation, you notice that you have tons of flexibility. You know what k is, and everything else is up to you to pick. So you can make all kinds of choices. So now you can look at that and play around, and you'll actually see that there's a whole bunch of different things you can do to pick values that solve this equation. And the one I did is to say that we'll actually arbitrarily pick 3 things which are both blocks of x1 and 1 block of x2. So now I've pinned down this value, and this value. And at this point, I'm going to solve for this value. And at this point, I can solve for it uniquely. And the way I do that is to use the inverse cipher. Here, I leverage that I actually know what the key is, so I can easily compute this. So having created this value and this, and move this to the other side, I get this here. And when I take ek inverse, I've solved for x21. So everything else pinned down, this solved for, and we have a collision because the equation is true. Okay, so does that make sense? So usually that's the kind of approach you'll use, meaning you'll just write some equation, understand for yourself which variables you control, which is often basically everything, and then solve it. And you have to just look for ways to solve these equations. Okay, here's one that's a little more interesting, and you can try that. Now, we developed hash functions as families, so they're allowed to have keys. But it turns out in practice, they often don't have a key, and that makes them what we call keyless. From the point of view of our formalism, we can view that as saying that the set of keys is just the empty string. And so there's only one choice of the key anyway. And so when you write H, you may as well drop it. So instead of writing this or this, we just write H of x. And so that's now an understood convention. And indeed, functions like the MD, SHA-2, and SHA-3 series are all keyless in this way. But you can still talk of finding collisions in the usual way. Okay, so so far we've only made attempts to build hash functions that didn't work. So maybe it'd be good to see something about how it would actually work. So we can look at what cryptographers do. And here we're going to proceed just as we did for DES, which is, I'll just show you what people are doing. And it looks like, a bunch of fairly weird steps just to get a sense of what goes on inside these functions. At some point, we'll see that many of these steps have quite a bit of structure that we can understand. But in the end, there will be some sort of magic. So this is the SHA-256 function. So just to show how central it is, this is the government standard that standardizes that function, and it's used everywhere now, and in particular you use it. And so the standard tells you all the details of the design. And so here it's defining the whole series. Remember the SHA-1, 224, 384, etc. And as part of that, it also defines the 256 function here. Now, the fact that's in this standard means that every detail about the design is public. So it's not like anything is hidden in the actual design, and the purpose of that is anybody can implement this. So if you want to write code for this, you can do that. And in particular, that means the attacker also knows it. So another thing to remember when you do any of these problems is that the designs of the functions themselves should be viewed as public. Okay, so this hash function has 256-bit outputs. That's the reason for 256 here. It's keyless, so we won't have a key space here. And what is the input space? It's, in some sense, intuitively strings of arbitrary length. But technically, there's a restriction. They have to be of length at most 2 to the power 64. And the set of those strings is written like this. The reason we think about it as everything is this number is so big that the likelihood that my giving SHA-256 an input above that length is pretty much null. So you can think of it as taking any input. So now what does the function do? You give it this input x, and the first thing it does is it pads it. The purpose of the padding is to ensure that the length of m is a multiple of a block length, and the block length here is 512. So we've often done the operation of breaking something into blocks, but to do that, this has to have length a multiple of the block length, and in practice that may not be true. So in this design, they do some padding first to make sure it's true. But once it's true, you break it into blocks. Here we've let n be the number of blocks. Okay, so now we're going to define certain constants. There's 8 of these constants, h0 up to h7, and they are words which are hardwired into the design, and they're 32-bit words. Having done that, I concatenate them all, and I get 8 times 32, which is a 256-bit string. And I call that h0 because I'm going to have many other h's. So this is a kind of 256-bit starting point. Now what the design does is it comes to the main part where it appeals to a subroutine, which I write as SHA little font, little small letters 256, and that's called the compression function. That function maps strings of this length to 256-bit outputs. So unlike this function, which has very long inputs, this has inputs which are only a little bit longer than the output, 512 bits longer. And what you do with this is that you take one block of the message and the current h value. So when I is 1, you take the first message block and this h value, and you apply the function, and you get out some 256 bits. That's the next h value. And then you keep going down the message and generating h values one after the other, and the last one is returned. So kind of this is called compression because you're slowly walking down the input and compressing it block by block. Okay, so that's the design. And now again, it's just some design, right? It's not like for example, it's not like we have a very good reason why this constant looks like this. So so then here are some details. This is a description of how that padding function worked. Remember, it took an arbitrary length string. It wants to produce something whose length is a multiple of 512. And the idea is, so it turns out that it's not the case that you just want to do something like 0 padding. That wouldn't be secure. So the way they do the padding is they take the original x, and at the end of it, they want to put the length of x. So they compute the length of x in 64 bits, and they stick it here. And that's kind of what they want, but then the issue is that you have to make sure the length of this whole thing is a multiple of 512. And the way they do that is they stick a 1 here, and then here they just put as many zeros as it takes to bring the length of this to a multiple of 512. And it turns out you can compute that number, and this is the formula. Okay, so that tells us how padding works. Now, we remember these weird constants, and we could ask, well, how or why are they getting them? And an interesting thing about SPA256 is that they don't just give them to you without explanation. They actually tell you how they got them. And the way they got them is that they looked at the first prime numbers, so the first 8 prime numbers, and took their square roots. And that gives you a fraction or a decimal. And then they took some bits of that expansion, and that was how they obtained these numbers. Yeah?
So is SPA256 just for like compression, or is there a way like that?
No, it's just for compression. So in particular, you can't go back, right? Because when you're compressing, there's no unique way to go back. And it's actually even computationally infeasible to go back. So it's hard, it's actually hard to even find any pre-image of an output. Okay, anything else? So now when looking at something like this, there is some curiosity about it, in the sense that why are they doing this? Why would your constants be obtained by taking square roots of prime numbers? Why don't they just pick something at random and then stick it in the code? And there you get to things that have come up in cryptography over time. And one of them is that there have been cases that standards have been subverted, meaning the standard was created, let's say, by a government agency who, through choices like constants, planted some kind of backdoor. And then the government was able to break the standard, but other people weren't. And people have become worried about stuff like that. And in order to show that nothing like that was happening, they said, you can check that these constants were done in this way, and hence there are not any backdoors. But actually, I'm not sure that they officially claim that that's why they did it, but this is what people speculate. Okay, so now let's take a little bit of a further dive into it. And remember that the heart of it was the compression function. It's kind of like DES, where there was a Feistel structure at the high level, then there was an F function at the lower level. So this is our lower level object. So this takes a message block of 512 bits and a 256-bit value that we call the chaining variable, and hashes it down to 256. And how does it do that? Well, we come back now to our friend block ciphers. What this actually does is that internally it defines its own special block cipher, which we'll call E SPA256. This one has a 512-bit key and a 256-bit input and output. So what you do then is you use the message block as the key and the chaining variable value as the input, and you get an output. That output is 256 bits, so you break it into 8 words, each of length 32. And you also take your original chaining variable V, which is 256 bits, and break it into 32-bit words. And now we're going to add the output of the block cipher back into this input in this way, through additions that are actually modulo 2 to the 32 on every word. You put all that back together and you have your 256-bit output. And that's it. That's how the compression function works. And again, this turns out to be a relatively well-accepted high-level design. So, well, we're nearly done. We have to then see how the block cipher works. But there we start seeing magic. So I'm not going to try to go through that in detail. It's rather just that you look at this and you get some high-level sense of maybe a few things involved. So one of them is that as with most block ciphers, there are rounds. So DES had 16 rounds, AES had 10 rounds. This thing has 64 rounds. And what happens in the rounds? Different bit shufflings, rotations, additions all mixed up together and works out in some way. So again, I don't understand enough of it to talk about details. Okay, so some final remarks are that this description omitted a bunch of stuff. For example, in the last slide, it invoked functions which I didn't say what they were, but again, the standard will. So you can go into the standard, and if you like, and you'll find all the details there. There are further constants, and again, they're derived in similar ways, not square roots of prime numbers, but this time cube roots and fractional parts. So you can easily calculate all these things. We can try to find one of these, but you can do a search for a calculator for SPA256, and you can type in something you want, and calculate it, and it didn't seem to want to give me an output. Very interesting. Okay, that's not doing very well. I wonder why. Okay, let's try this one. Well, maybe it's a question of how much input you give. Yeah, here it got one. So yeah, you get some weird output. But you can see it's, looks pretty fast, and you can do it on anything. Okay, so now we've seen what these things look like. A natural question is, well, why do we want them? Well, earlier I mentioned a bunch of important motivations, and indeed through these are very popular in practice, things like certificates, HMAC, Bitcoin, etc. But actually none of these applications are within reach for us now. We'll see certificates after we see public key cryptography, and HMAC in the next chapter, and so forth. So in order to have something concrete, I thought I could illustrate an application to passwords. So this is also actually a pretty big use case. Namely, we all have passwords, and if you know how it works, then when, say, you log into Google or any of these services, you will be have created a password with them, and then you will flow that password to them to authenticate yourself. Obviously, you wouldn't want to do that in the clear, so you would flow it over a secure channel like TLS. And then the idea is that the server will verify, because it has a stored copy of your password, that this matches, and if so, then you're authenticated. So that would be the naive way of doing it. But the problem is that even if you trust the server, you've all heard of data breaches. So every now and then we get informed that some server was breached and all your stuff and passwords were compromised and so forth. And indeed, the threat there is someone finds the server's table of passwords and thereby learns your password. So as a result, they don't do this. And what they actually do is that you have a password just as before, but what the server stores is its hash. So this is some collision-resistant hash function like SPA256, and the server has the image of your password under that. So why does this help? Because if the attacker compromises the server, it only gets the hash value, and at least if your password is well chosen, it should then have a hard time recovering the actual password. How about the authentication itself? That actually doesn't change. You do send your password in the clear over TLS to the server. The server hashes it and checks that it matches this, and then discards this, so it doesn't store it. So that's actually how all authentication is happening now up to details. But it would be incorrect to kind of close the story without the warning that despite this, these data breaches are extremely successful in the sense that they find quite a lot of passwords. And the reason for that is that many people choose bad passwords. So they choose them in low entropy ways from pools which are easily exhausted. And then just through exhaustive search, your adversaries can effectively invert H and find the password. Okay, so we're now moving on to security analysis. So we're going to get to collision finding attacks. And the basic attack is that our old friend, the birthday attack, works here. In fact, hashing is probably the most popular application of the birthday attack and phenomenon in cryptography. So I'll again recall that when we use the birthday attack, I want to appeal to algorithms like one for finding list collisions. And recall what that means is if I have a list of n-bit strings and I pass them into this algorithm, it will return a pair AB. And if A and B are non-zero, it's telling us that the Ath and Bth elements in this list are equal. They form a collision. And if there's no collision, it'll say 0, 0 to tell me there's none. And we know we can design these, let's say, through sorting, and this is the running time. Okay, so then here's a generic attack on any hash function which uses the birthday problem and finds collisions. So we have our fixed family. I'll again go back to the general case where it's a family. We'll assume the domain is larger than the range. So the size of the domain is at least 2 to the n. And the attack is parameterized by some value q, which is kind of the effort or number of trials of the adversary. So the bigger the q, the better it'll do. We're writing this in our games. So A gets input this key. And now it just wants to find 2 inputs for H with the same output. And its strategy is quite natural and simple. It takes some arbitrary inputs. So it picks them, say, at random from the domain, and it picks q such inputs. And it just evaluates the hash function on each of them. It can do that because it knows the key, and H itself is public. So it has code to do this, and it gets a result. And now it just asks itself, did this find a collision somewhere? In the sense that I have this list of outputs of H. If any 2 of them are the same, I have a collision. So let me just check if any 2 of them are the same. Well, this find list collision algorithm does that. It'll return ij, which is either 0, 0 or a collision. So if the algorithm says, sorry, you are not lucky and there's no collision, meaning this is 0, 0, then it's going to fail. But if it says, if it gives back a non-zero, 0 value, it's saying that y sub I equals y sub j. But in that case, xi, xj is a collision. That's what it means, because hk of xi equals hk of xj. So we found a collision. Now there's a little caveat. It's not really the case that you found a collision if your inputs themselves were equal. So we'll test to make sure that isn't true before we return the collision. Okay, so that, I mean, it's pretty clear that if this outputs xi, xj, it is a collision. So the next question would be, how long does it take and what's its success probability? So we can compute the running time quite easily from the prior slide because we know how long this takes. And so it runs this once and it computes h q times. So you have q times h here, and qn log q is the time to run this algorithm. And notice that it does depend on the running time of h. And then you have to see how to apply the birthday paradox and analysis to see that you can effectively view this as throwing q balls into 2 to the power n bins, and through that see that you get a roughly quadratic in q and inverse in 2 to the n growth in the success probability. And with our lemmas about lower bounding and so forth, you get an advantage for A that looks something like this. So in particular, the higher the Q value, the bigger the advantage. So, and the salient point then is once Q hits about 2 to the power half of this value here, you will have an advantage that's a constant, and that's viewed as a break. And so we have a conclusion from this, which is that you can find a collision on an n-bit output hash function in about this much time or this many trials, where a trial means a computation of h itself. And the important thing is this is 2 to the power half of this output length. If you have 128 bits here, it's 64. If you have 256, it's 128. So it is doing something non-trivial. If you want the running time in detail, you have to go back to this formula and plug in everything. So if Q is 2 to the power n over 2, and then log Q is n, and so forth. And so if you simplify, you get something like this. So it'd be good if you, when you go back over this, you check all those details, you check that you see why, if this returns something, it is a collision, and so forth. Because this is the most basic possible attack on hash functions. Okay, so any thoughts about that? Okay, so let's see what the consequences are. Everyone knew that this attack is possible at the time they were designing the functions, and it's unpreventable. It's once you have a function, you can always run the birthday attack. So the way they try to defend against it is simply to pick an output length big enough that the birthday attack time looks infeasible for an adversary. Back when the early MD functions were designed, which is like the early 90s, an output length of n equal 128 was chosen because the estimate then was 2 to the power 64 time for the birthday attack was prohibitive enough. But that, after a while, as computers got faster, people started seeing that, okay, maybe that's not quite good enough. And the next idea was, let's make sure the adversary needs to run at least this much to find a collision. Well, if that's the case, we need the output length to be double of this. And so they went for an output length of 160. And that was what SHA-1 did. And the whole point of these succession of functions going further is, in fact, to increase that limit and the time it takes to find a birthday collision. So for SHA-256 with 256-bit outputs, you need 2 to the 128 time. There's a SHA-512 with 512-bit outputs, so now you need 2 to the 256 time. So they're making the birthday attack more and more difficult. With the new SHA-3 series, you see the same thing, that you have variants and corresponding birthday attack times. So that's pretty much where we stand in terms of hash functions. Okay, so now we're going to get into a little more about how you actually build and justify these things, in particular what people have been doing, and it'll involve looking at the inside of SHA-256 a little closer. So you remember there we had something called a compression function, which was written as lowercase SHA-256. So now we'll abstract that out. This is a function in the keyless case here that takes an input whose length is a block length b plus some output length n and hashes it down to n bits. So in the case of SHA-256, the block length was 512 and the output length was 256. If you look at the SHA-512 function, it has its own compression function. It turns out they use a 1024-bit block length and a 512-bit output length. But there'll be some values like this. We will refer to the n as the length of the chaining variable, or as also the length of the output, since they're the same. Okay, so the compression function turns out to be the central object. So a lot of what we're interested in is designing that as well as possible. So so we're going to study that a little bit. So the way it's written here, its input is a single string of length b plus n. But I usually want to break it into parts. So I'll see it as b bits, which I call x, and n bits, which I call v. And view this as a message block and this as a chaining variable. So when we write it, we could write it like this, h applied to the concatenation of the message block and chaining variable. But pictorially, it's kind of nice to see it like this. Although h has formally one input, you kind of see these two things separately. You see the x coming in from the top, the v from the bottom, and the output is kind of an updated version of this input over here, formed by compressing both of these. And so this picture will be useful to play around with compression functions. So what people do with these is they design them to be collision resistant. So the design goal is the same as for the hash function globally. It should be hard to find a collision. And a collision means two xv pairs with the same output. So once you have or are able to find one of these collision resistant compression functions, what designers have done is give you an automatic way to lift it to a hash function. And this has been an important theme, and in particular used in SPA-256. So the way it works is that suppose you have this compression function with its given block and chaining variable lengths. And what we're going to do is build a hash function from it in some kind of automatic way. And it will have a much bigger domain. The domain will be the set of all strings up to some large maximum length, where that large maximum length is something like this, where this little l is something smaller than the block length over here. So in particular, now we can recall that with the compression functions we know, like this, you can do something like this and get corresponding hash functions. However, I haven't said how you would go from the compression function to this hash function. And there's a specific way of doing that, which is called the MD transform. And the reason that's important is that we have this guarantee that it works. And this is another important example of having things like proofs of security, which is that there's a fact which says that if you have a compression function that's collision resistant and you build this in this way, you're guaranteed that what you get as a result, the hash function, is itself collision resistant. So that's a pretty powerful conclusion, and SPA-256 is designed in a way that leverages this. So given how central this is to design, we'll kind of look at it in a little more detail. So the setup is the same here as before. You're given this compression function, and you define your domain for the hash function. And the goal of our transform is to take the compression function and automatically turn it into this hash function. And it must do this in a way that preserves collision resistance. The benefit of doing this is that now the security of hashing long inputs doesn't have to be considered by itself. Effectively, it's saying once you know you can securely hash short inputs, you are automatically able to securely hash long inputs. And so you don't even need to bother about trying to find a weakness in this hash function, because the only way it could arise is there was a weakness in the compression function. So you may as well focus your energies on that, and that'll be a little easier. And this was such an appealing fact that it's used in the designs not only of MD, but the whole SPA-2 series. And so SPA-256 uses it. But when they went to the most modern series, SPA-3, they actually changed that. So, I'll detail a little bit how this transform works to build hash functions. So remember, we start with this compression function, and there will be 3 steps. In all of these, it would be useful to use this to denote the set of all possible message blocks, so b-bit strings. So first we'll extend the compression function to something called a cascade, which is actually a family. It takes an n-bit key and it takes inputs which are strings over this space and hashes them down to n bits. Once we have that, we just fix a constant value, just like SHA-256 bits did. And finally, we have a way of taking messages from our space and through some padding, making them into sequences whose length is a multiple of b over here, meaning they fall in this set. And those three ingredients will yield MD in a quite simple way. And so this is the picture that kind of shows how it works. So if I have an input to hash, I view it as a bunch of blocks, each b bits long, and all I do is iterate the compression function on them. That means I start with some fixed value, eat up the first block, get something of length, same length as k, then the second block, and so on, and at the end I get an output. This is actually not the hash function. This is what we call the cascade, which we denote H star. The k here is an input to it, and this is just the code that shows you what the picture does. So this is a way to take a string whose length is a multiple of the block length and bring it down to n bits. So that's kind of the core of what we're doing, but it doesn't quite solve the problem, because the difficulty is that this H star is actually not collision resistant in general. So we need a little bit more work. And so this is the final design of a hash function with the MD paradigm. All it does is it takes the message and through some encoding that we could also call a padding, it creates in some special way a string whose length is a multiple of the block length. And once you have that, you run the cascade, and as a key, you just use some fixed constant, some hardwired fixed constant. And that's it. That's your hash function. So simple enough design, and we can look at more details. For example, this is how the message encoding is done. And the reason to see this in a bit more detail is we recognize that this is exactly what SHA-PAD did. So in other words, it takes an arbitrary length message, sticks the length of the message at the end, encoded as a binary string of some length, and then puts a 1 and a bunch of zeros, and enough zeros to make the length of this a multiple of b. Okay, and this is kind of the punchline, which is the thing that it's good for you to understand. It doesn't matter if you don't understand the details or remember the details of how MD works, but the important thing to remember is that this theorem is true. So what the theorem says is, if you have a compression function and you build our hash function in the way we just described through the MD transform, then if the compression function was collision resistant, so is the hash function. And in the theorem that's captured in this constructive way, like a proof of security, it says if you hand me some attacker trying to violate security of the hash function, it will have some advantage. But I can bound that by the ability of some alternative attacker to violate collision of resistance of this function. And the way the proof works is that it will tell you how to go from this adversary to this adversary, as reflected in saying we can build over here. The way you interpret this is to say we are willing to assume that this little h is collision resistant. That means that this can be seen as small. But if that's the case, the inequality says this must be small. And that means that the advantage of a sub h against big H was small. And so the big function is also collision resistant. So, so this justifies, for example, yeah?
Can you clarify the difference between compression and hash?
So compression functions take fixed length inputs. So here, for example, with B being 512 and N 256 is just what, 700 and something bit input. But hash functions take very, very big inputs. That's the only core difference. So it's only a question of how big the input is. But the nice thing about the process is that it's saying that the problem you really need to worry about and solve is how do I hash short inputs? Because once you do, the rest the MD transform does for you. So we're done with that part of it. We only need to worry about compression functions. Okay, so we've gotten pretty far now into understanding the design of something like SPA256. And effectively, we've brought it down to one thing. I need to have a good compression function. So how do I design that? Well, we kind of saw what SPA256 did. It used a block cipher. So let's try to do the same thing. So let's say I have a block cipher where the message block length is the key length for our block cipher, and the desired output length for the hash function is the block length of the block cipher, which is what SPA256 builds internally. How could I use that to create a compression function? I want to hash data. So this is the most obvious design. It says the compression function takes b bits plus n bits, and if I want to use the block cipher, well, it takes a b bit key and n bit input. So the obvious things are plug this into here, plug this into here. And that gives you a perfectly valid candidate compression function. So that would be the first thing that comes to mind, but then you have to ask if it works. And when we study whether it works or not, as we looked at when we talked about collision resistance examples, the way you set up that question is always like as an equation. So suppose you want to think whether you can find an adversary violating collision resistance of this H. What I'm saying is the adversary needs to find two inputs, but each input is two things. So your first input will look like this, the second input will look like this. And what equation must they satisfy? That the function output is the same, and that equation looks like this. So now we look at this equation and say, I need to solve it. But we have tons of flexibility. I get to pick all four of these things in solving it, because both these inputs are under my control as an attacker. And once you see that, you notice that it's quite easy to solve. In fact, you don't even need all that flexibility. So what I did here, for example, is I fixed the message block or key inputs to some constants, and I even fixed this value to some constant and just tried to solve for V2. And how do you do that? Well, since E is a block cipher, if you know X2, you can run EX2 inverse on this and recover V2. And so that's what's done over here. Fix some value for X1 and X2 and also V1. So this is determined, and here. Okay, back again. Okay. And so you run EX2 inverse and solve for this, and then you've satisfied the equation. And as usual, if you have to do it formally, you have to write your adversary in pseudocode. And so that's so that you have an example of that. That's detailed here, right? There's no key going in because this is a keyless function. There are two outputs coming back, which are both possible inputs for H, and we know this equation is true, so they'll form a collision. Okay, so not much more to say here. The way this gets wrapped up is that people looked at this attack and said, okay, is it unsurmountable? And the answer was, there is something, little change we can do which will actually remove the attack, which is that when defining the compression function, after as before doing E with key X and input V, I just XOR V back in. And you might think this is a very small change and it shouldn't make a difference. But if you go through the exercise and try to solve your equation again, it's actually not at all clear you can do it. And the reason is that when we try to solve for V2, the previous attempt won't work because it occurs in two places. And so it's not clear how you're going to get it out of the equation in that case. So, of course, there may be other ways, but the fact is no one seems to have found one. And so in the end, this works, and this is called the Davis-Meyer compression function. And that's what we saw inside SHA-256, up to details. Okay, so I think I better switch now. So what I wanted to do is talk about the practice quiz. So first off, let's see. So note that that's up here, right? So there was a document posted on that, and that gives you both information and practice problems. So so it's next Tuesday, and for the whole class, and we will post seating assignments as soon as we can. And so you look at that before you come in, and you'll see a mapping of ID to seats, so you know what seat to sit in. You're allowed, remember, to have hard copies of the slides, but only the ones given out in the class. So those can be picked up outside this room of the CSE building. So if you haven't already, then before the quiz, be worthwhile to grab yourself a copy. Now, then as far as practice problems go, our policy is that we're not going to post solutions. The reason for that is that it doesn't help you to see someone else solve them. What really helps you is your own attempts. And if you have somehow a way to not make those attempts and just look at solutions, well, then you won't go through the learning process that actually helps. So you have to earn solutions. What that means is you can make attempts and hopefully correct ones and check your solutions with us. You can do that via private Piazza posts. If you don't have Piazza, send email or whatever. And probably Rishabh will also try to cover some of it in discussion, which is just before the quiz. The syllabus has been restricted to be only up to and including pseudorandom functions. So in particular, symmetric encryption is not on the syllabus. And I did that just to make things a little easier in terms of the volume of stuff you have to process and understand, right? So it's the earlier part of the class, it's less material, only 2 chapters. So hopefully you have more experience with that at this point, and you can study it in depth and so forth. So these instructions will be repeated on the quiz, namely that the rules is only those hard copies, so don't expect to pull out a phone or any device like a computer, calculator, or whatever. And try to write neatly, so not at random places on the paper, but kind of left to right, top to bottom, so we can read it, and otherwise who knows what we'll find and miss. You, of course, can benefit from scratch paper. Just use the back of the exam. There will be ample blank pages there. You do your scratch work there, and then put the final answers on the test itself. And leave your scratch work there. You can just submit it with the exam. Make sure you look at whatever notations are defined. Sometimes I get questions in the exam, what does this notation mean? Well, it was on the first page. So if you had actually read the first page, then you wouldn't have to ask. Other notation is already in the slides. As a result of that, it's extremely unlikely that you will actually need to ask what notation is, right? It's going to be somewhere. Okay, so any questions about general stuff before we look at practice problems? Yeah?
Is it okay to take a note from the hard copy?
Not notes, no. So it shouldn't be annotated. If you already did it, you can grab a new copy. But you can have bookmarks. So for example, if there are particular slides you think are important, you put a marker so you can get there quickly. That will be okay. Okay, so the slide has 5 practice problems covering topics in these chapters. And I have a suggestion for you. So today is Thursday. So Thursday, Friday, Saturday, Sunday, Monday is 5 days before the quiz. I suggest you do 1 practice problem a day. It's a good sort of discipline to set yourself. Don't leave it all to the last minute, and that way you will be on track. So actually make like a calendar entry or something, and have like a pace or tick it off and say, okay, every day I will do one practice problem, okay? And then that'll get you well prepared. So now when you look at the practice problems, how do you start approaching these things? You first of all pay careful attention to everything that's written. So here it says, let this be an integer. And I have actually clarified what that means, but that doesn't always happen. You may not be always given that clarification. So you should understand that when a statement like this is made, it means that you don't get to pick it. It's a fixed value that you have to treat as a variable. It's not something where you decide what it is. Okay, that distinction makes sense? Because what happens sometimes is people hand back solutions to this in which they've set n equal 2. Now, that's not a solution. Okay. Now, what the problem does is it gives you a way to take a family of functions E and build another one called E star. This is a transform. Given E, here's how E star is defined in terms of E. And what it does is it swaps the order of inputs. Okay. It's a well-defined object. You can do that. So now what do the problems say? They talk about block ciphers. You notice there's nothing here about security. It's only about block ciphers. So when you see that, let's say you're either on a quiz or you're trying to do this, what would be a good step to take here? Yeah? Yeah, yeah, good. So a natural good step would be you go and find what a block cipher is, because if you don't know what that is clearly, then you're going to have a hard time with the problem. So go back and you review the definition, and the definition tells you exactly what a block cipher is. So now that you know that, you go to the problem and you see what it's asking. It's saying present in pseudocode a block cipher E with a certain property, namely when you do this E star on it, you get something that's also a block cipher. So you have to parse that. But at the end of it, what is it you have to present? I mean, what do you have to build here? You're being asked to give something. So how do you, I mean, what is it you're asked to give? And what do you have? Huh? Yeah, but defining what? Which one? Okay, and okay, I mean, how are you going to build that? Can you build a block cipher? Okay, yeah, how's that? You want to tell me an example? Yeah, good. So, in other words, there's an infinite number of these things, and they can be anything you want. You get complete control over it. Okay, so they're saying build it, but it's not arbitrary. You then have to look at this and make sure that's also a block cipher. Okay. And here you do the opposite. You have to give a block cipher E where E star is not a block cipher. So now the things that people get confused about is they may start designing this, but you're not designing this, you're designing this. Once you design this, this is automatically defined. Okay, so your choice is here, not here. But you have to do this in such a way that something happens here. But all this you have to learn to parse, okay? It's all mathematical language. It should be something you can read the problem, parse, and quickly figure out, this is what I need to do. And so you have to learn to play with figuring out what's given and not given. You can't on a test say, am I given this? That won't get an answer. Okay, so the next problem says you're given a block cipher E, and F is defined in a certain way, and it tells you what is its key space, input space, output space. And this is something you've seen many examples of before. And the job is that you have to give an adversary with certain parameters. It has to achieve a 1 advantage and so forth. Okay, so suppose you see this, then again, what would be a good first step? I mean, he already told you for the prior problem, so again, what would be the good first step? What would you do? I think that would be like a second step, but it's okay, good, that's fine, you're heading ahead. But what would be a good first step? Yeah, so what slide do you want to look at, and how do you know which one to pick? Yeah? Yeah, and which game do you want to look at? Uh-huh. How did you figure that out? Right. So you look at this and you say, okay, that's what I need to look at. So now you go back to this chapter and you go and see what those games look like. So you find them somewhere. And that's it. So now you know this is the game that you need to have your adversary play, right? Okay. How do you pattern match things here? So what is this E in our problem? Yeah, it's not E, right? It's the F that'll play that role. So now you have this set up. Now you know what you want to do. Now I think what he said is a nice second step, right? Why don't you make a picture? That's often a good way of like kind of getting an intuition about what it's doing. Now, once you've found the game and you know what you have to do, you're going to need a little creativity, and there's no getting around this. And that's kind of the things I talked about the class, right? It's not the case that you're going to be given methods which you can blindly follow and will always get you to the outcome. At some point, there'll be a little bit of creativity needed. And you have to do that here. You have to think, what is it that's wrong with this that results in my ability to get an adversary? And once you get that, then you write the pseudocode. Okay? So now you should have the template. So now there's another problem like that. So how do you approach this? First off, read slowly from the beginning and pay attention to everything. Everything means, what does let mean? What do you deduce from the word let when you say E is a, huh? Yeah. So that's known to you. It defines notation here. If you decide to not read this and go here, you won't know what this means. And then you'll ask in the quiz or something, and we'll say we can't tell you. But if you read the whole thing, then you'll know what it means. Now it defines some other function. You have code for it, but what's another thing to pay careful attention to about this function beyond the code? So that would be this, right? So don't neglect to look at what these sets are, because they're a very important part of what the function is. If you don't understand what those are, then all kinds of things get confused. Okay, now that you've maybe understood that, you can say, okay, here's the code. Now you follow the same steps as before. So which game are you going to pull up here? KR, right? So you go back again and you say, okay, where's the KR game? So you find it. And that's what it looks like. So now you know what your task is. Okay, so now you have to get the adversary. You have a hint in running time that will tell you some place to look. But again, at that point, you have to be a little creative. You have to look at this formula and say, okay, what is it that's not perfect about it, and how will I exploit it? Okay? So, any thoughts so far? Yeah?
Maybe like C2 is like kind of manipulated since it's
Mm-hmm. Yeah, but that all you'll figure out. So, yeah. It's a good start, right? You're seeing there's something weird there. Okay, so let's go to the next one. So this is a similar thing, but a different metric. So you start noticing also that all of these things look very similar. There's the same let E be something, right? So hopefully by now you know what that means and you're used to it. Okay, you've seen it like 10 times. There's again like some notation defined inside the problem, so you pay attention to that. And there's another function family defined by some code. So let's go through steps again, right? So what's your first step with regard to slides? Yeah, so this time you notice that it's the PRF thing. So you go to this chapter and find the games. So this is a page it would be good to bookmark, right? These are why I said those bookmarks are useful. So this would be a page you can bookmark because you'll be coming back to that. Okay, and then it tells you you have to give an adversary with a certain advantage, and it tells you how many queries you're allowed to use. And this is also a hint because it's saying that many will suffice. And now you notice that this explicitly has two parts. So one is it asks for pseudocode, and the other is it asks for proof. So now, again, you have to be a little creative. You have to think what's wrong with this and turn that into your adversary. Now, what would a proof look like? Do you have any idea, or any idea how you'd figure out what a proof would look like? Like, where would you look to see what a proof would look like? Good. Yeah. So that's the right way to do it. But what I'm saying, what I was suggesting, there's something that helps you get to where you already got. But if you haven't got where he got, how would you know? How did he know that? Like what? You have some resources, right? Where could you go to look at to get the answer of how you write a proof? The definition doesn't tell you how to write the proof, right? The definition looks like this. Yeah, so you can look here. Here's a KR example. It gives you a construction, and it says, here's an adversary, what's the advantage? And then it goes through, oh, this is KR, sorry. So we should look at PRF. So here's an example. It says this exactly the same type of problem. You have a family, design an adversary, what's its advantage, okay? So it shows you, what do? You write your adversary, that's part one of the problem, and then you go through the steps of computing the advantage like this. So you compute this probability, compute this probability.